वेलकम बैक फिजिक्स एंथुसियास्ट। आज का वीडियो है MCQ पर ऑन द टॉपिक मूविंग चार्ज एंड मैग्नेटिज्म। लास्ट सैटरडे आई कांट पोस्ट द वीडियो बिकॉज कुछ ज़्यादा टेक्निकल इश्यूज हो रहे थे एंड सम पर्सनल प्रॉब्लम्स हेल्थ साथ नहीं दे रही थी। सो या आई नो आई एम लेट, योर एग्जाम्स आर ऑन आवर हेड, बट ओके। अगेन क्वेश्चंस बहुत अच्छे हैं, लास्ट टाइम रिवीजन के लिए लिटरली बहुत बहुत अच्छे हैं। सो लेट्स बिगिन विद दैट। Okay, students, so let's begin with that. Moving charge and magnetism. I've actually recorded this whole video and due to some technical issues, 2 बार पता नहीं क्या हुआ कि वो आया ही नहीं. So that is why last week I can't post. But okay, इस week ज़्यादा मैं post कर दूंगी जिससे कि इस week सारा तुम्हारा ही complete हो जाए. Okay, so the first question is, if the conducting wire carries a direct current through it, the magnetic field associated with the current will be. ऐसे तो मैग्नेटिक वायर हम पतली लेते हैं, बट इफ नॉट तो इसके पीछे का जो मैकेनिज्म है वो मैं ऐसे समझा सकती हूँ कि सपोज एक कंडक्टिंग वायर है, थोड़ी सी बड़ी है एंड इट कैरीज सम करंट आई, लेट्स से ऑफ रेडियस a. Now there are two positions. One is outside the wire and one is inside the wire. So for the outside the wire, we take a Ampere's loop, and using Ampere's law, which is B dot dl is equals to mu naught I enclosed, we can simply say that B, and dl is the circumference of this loop, which is 2 pi r mu naught I, and total I flowing in this is I only. So B is equals to mu naught I over 2 pi r. Fine. And if there is a point inside this conductor that is somewhere at this r, then we consider an Ampere loop, and if the current is uniform, then we have to find the current density, that is current per unit area, that is pi, let's say its radius to be a, pi a square, and then we multiply it by the area of the Ampere's loop. So I am explaining you the mechanism. It is same as Gaussian surface type, the thing we do in the Gauss theorem. And then B dot dl, and here the dl will be 2 pi r only, is equals to mu naught times I enclosed, and I enclosed will be IR square by A square, and then R and R will cancel, and B comes out to be mu naught IR over 2 pi A square. So, and at the center, the R will come 0, and your B will also become 0 at the center. So there will be current inside and outside the conductor, but if you consider a case when the wire is very thin, and in that scenario you can consider that all the current is on the surface of the wire, and the magnetic field will only be outside the conductor. Okay. So in this particular case, it is the C option, only outside the conductor. So we are assuming that all the current is on the surface. But I have taught you the mechanism that they can be inside, outside. The current will be both at inside and outside. Okay, next. Question number 2. A region has a uniform magnetic field in it. Uniform magnetic field. A proton enters into the region with velocity making an angle of 45 degrees with the direction of magnetic field. Okay. Always remember, whenever a charged particle, electron, proton, enters the magnetic field in its direction, either parallel or anti-parallel, it keeps moving along its same direction. Okay, it moves in a straight line. If it comes at an angle of 90 degrees with the magnetic field, then it starts moving in a circular path. That is, its trajectory is circular. And if it enters the magnetic field at some angle, then it has two components, parallel and perpendicular. The parallel one moves it in a straight line, and the perpendicular will make it in a circular motion. So the path of the particle which is entering the magnetic field with some angle would be helical. Okay, so there are 3 trajectories which a charged particle can have when it enters a uniform magnetic field. So here it enters with her velocity making an angle of 45 degree with the direction of magnetic field. So that means that it will move in a straight line and also in a circle. That means in a helical motion, that is helix. Okay. And when the object do helical motion, there is a pitch, and which we will discuss in next question. That is, two charged particles traverse identical helical path in a completely opposite sense में. तो helical path है. So there is a pitch. That means when the particle is moving like this, it's a helical path. The distance between this is a pitch. And the formula of pitch is basically 2 pi m v cos theta, because v cos theta is the parallel velocity upon qb. Now here they have asked that they are moving in a helical path in a completely opposite sense. Everything is identical, but the direction is opposite in a uniform magnetic field, which is B is equals to B naught K cap. So the options they have equal Z components of momenta. They must have equal charge. They necessarily represent a particle-antiparticle pair, and the ratio of mass by charge by mass is this. Okay. So here let's take Q by M to be out. This become 2 pi V cos theta over B into pitch. Now here 2 pi constant, V cos theta is also, and B into pitch. B is uniform, pitch is same because it's the same helical path. So V is constant, but since the direction is opposite, so one should be positive and other should be negative. So Q by M ratio should satisfy that the sum of both is equal to 0. That is, one should be positive and other should be negative. So the V should be negative and it moves in the opposite direction. So D is the appropriate one. Next, a current I flows through a long straight conductor which is bent into a circular loop of radius r in the middle as shown in the figure. The magnitude of the net magnetic field at point O will be. So you have this figure. You have one wire like this and it's a circular loop. Okay. So here we can divide it and we can find magnetic field due to these three parts, that is first part, second part and third part. So B total is due to all these three parts. So for the first part, you can use this. If the current is downward, then your thumb will point outward. So that means because of this wire, the magnetic field would be upward. Similarly, for the third also it is upward. And for the second, the current is moving in a anti-clockwise direction. So the magnetic field is this. So for the first wire, let's consider it as the semi-infinite wire. The magnetic field is to be calculated at one of its end. And the formula is mu naught I over 4 pi r. Okay. And it's outward. And this r is capital R because it is the radius, the distance. For the third wire, this one, third part, it is again mu naught I over 4 pi r. This plus, due to the circular wire, it is mu naught I by 2r. And it is cross. So we can add these two terms, which gives me mu naught I over 2 pi r. And this would be minus because of the cross sign. Let's take only the magnitude. And if you get, or you can take this one to be like mu naught I over 2r to be common, 1 by pi minus 1. Okay, so this would be outward, and if you take the inward one, then the minus sign would be there, and the answer would be option D. It is same, it's just the direction that matters. Okay, because this can't be true, this can't be true, and this is also. So only the D option is there, the minus sign is there, so it can change with the direction, because if you take cross, then this become minus, this become plus, so this become minus, this become plus, and it is same as option number D. Okay, so you can check the options as well. Biot-Savart's law indicates that the moving electron produces a magnetic field. Yes, Biot-Savart law states that moving charge, moving electrons produces magnetic field, and it has a formula of mu naught upon 4 pi I dl sine theta by r square. Now here you can see that If we multiply R by R, this become IDL cross R by R cube. This term into mu naught by 4 pi. Now, dB is the vector product of IDL cross R. That means, as per the vector law, that this dB is perpendicular to both IDL and R. That means B is perpendicular to IDL, that is current element, which is a vector quantity, and B is also perpendicular to the R, that is the distance between this current element and the point where we have to find the magnetic field. And if it is perpendicular to both, then the direction of moving electrons is opposite to the direction of current. You know that I is parallel to the velocity of electrons, anti-parallel basically. So, which states that magnetic field becomes perpendicular to the velocity of electrons. So B is perpendicular to V is parallel to B. Inverse cube law can confuse people because here it's coming R cube, because we have used that cross product. We multiply our vectors, but actually it doesn't follow cube rule. It follows inverse square law, R square. Okay, so don't confuse with cube rule. It is along the line joining the electrons and point of observation, or it is perpendicular. So A is the correct option. An electron is projected with uniform velocity along the axis of a current carrying long solenoid. Which of the following is true? So an electron is projected with a uniform velocity along the axis of a current carrying long solenoid. So you have a solenoid. It's very easy. The magnetic field is like this. It is uniform inside the solenoid, and the electron is projected with uniform velocity along the axis. Electron itself is moving in the direction of magnetic field, so it keeps moving in the direction of magnetic field without any acceleration. Because the magnetic field is uniform, so electrons will be accelerated along the axis. No, magnetic field cannot change the velocity. It only changes the direction of the electron, so it cannot accelerate it. So electron path will be circular about the axis. No, because it moves in the direction of magnetic field, so it keeps moving along that. Will experience a force of 45 degree. No, will continue to move with uniform velocity along the axis of the solenoid. Is the correct one. Okay, the next. A microammeter has a resistance of 100 ohm and a full scale range of 50 milli microampere. I don't know, there is some problem here. It can be used as a higher range ammeter or voltmeter provided resistance is added to it. Pick the current range. If you have to convert, it's a basically microammeter. So if you have to convert this ammeter into a ammeter, then a shunt resistance, low value of shunt resistance should be added in parallel. And for voltmeter, a high value of resistance should connected in series. This is a high value in series, so this should be for voltmeter. And for the ammeter, it should be lower range. It's both. It's parallel, so we can check the current range using the formula Ig is equals to shunt resistance, shunt plus galvanometer into full current. So S shunt, take 1, and G is this 100 ohm, that is 101, and the current is 50 microampere. Let's take, or milliampere. So 50 by 100 gives you 0.5 approx microampere, yeah, milliampere. So it should be around 5 milliampere around. Okay, you can use this formula to determine the range, and yeah, this could be for ammeter. Next, a current carrying circular loop of radius r is placed in the xy plane with center at the origin. Half of the loop with x greater than 0 is now bent so that it now lies in the yz plane. Okay, so you have a loop, and if it is divided like this, so they have asked the magnetic movement about and the magnetic field. So just remember, for the magnetic movement M, it is equals to IA. Now if the loop is half, area become half, and for xy plane, magnetic movement should be in z direction. perpendicular to the plane. So this is M1, which is basically M by 2 times of K cap, and M2 will become again M by 2, but its direction, if the plane is in YZ, then its direction should be I cap. So one is in K cap, another is in I cap, that is both are 90 degree to each other. So if we take the M net, then it would be M1 square plus M2 square plus 2 M1 M2 cos theta. Cos is 90 degree. So it reduces to only M1 square plus M2 square. That is M square by 4 plus M square by 4, 2M square by 4, that is M by root 2. Yeah. So M by root 2, that means it decreases. So magnetic moment now diminish. Does not change, no, it diminishes. And for the value of B, see, magnetic moment is diminishes, so B is also diminish. And you can see at 0, 0, Z, for Z is very greater than R, increases. No, since the loop is half, so using the formula of magnetic field, which is mu naught IA square by 2 3 by 2, and for very the distance is very greater than the radius, you can skip this, it's simply this. And if you multiply pi and pi here, then this pi a square would be area. Now the area is getting half, the magnetic field also decreases. So they have only given the increases and the unchanged value. So basically the magnetic field will decreases, and it has a relation with dipole moment, magnetic moment also in torque and energy, but there is no direct relation. But you can understand it using the formula magnetic field on the axis of circular loop. And yeah, so if we take the other part, when the plane is in YZ plane, so the other half is only in YZ plane, and they're also asking for at the Z point only. So only the other part, which is in XY plane, will give its value, which obviously decreases. Okay. The sensitivity of a moving coil galvanometer increases with the decrease in. For the next question, the sensitivity of moving coil galvanometer has current sensitivity and voltage sensitivity. So IS is basically NBA by torsional constant, and voltage sensitivity is NBA, and one resistance is also there. So if you increase number of turns, magnetic field area, sensitivity will increase. But if you increase torsional rigidity, it will decrease. So it increases with the decrease of torsional rigidity. Okay. Next, a voltmeter of range 2 volt and resistance 300 ohm cannot be converted to an ammeter of range. Let's simply calculate I, which is V by R, which is 2 by 300, and 2 by 300 is what? 0.6 milliampere. 6 milliampere, 6 point something milliampere. इसको डिवाइड करके देख लेना. तो इसके नीचे the range lower with this value cannot be converted. The above can be converted because this is a limiting value. Okay, so 5 milliampere cannot be converted, the higher ones. Okay, next, if an ammeter of 4% of the main current is passing through the galvanometer, if the galvanometer is shunted with a 5 ohm resistance, then resistance of galvanometer. So you can use the formula here. You have to calculate the resistance of galvanometer. GS is equals to IgG over I minus Ig. Okay, you have to remember the formulas. Or if you have just remember this one, we have done one before. This formula, you can convert it and you will get this formula. Just revise one, learn one, and then you just only have to transpose the values and you can get. Okay, so Ig is the current in the galvanometer, which is 4% of the main. So let's take it 4. And the shunt resistance is what? 5 ohm is equals to 4 times of G. And if you are taking 4% as the current passing through galvanometer, then the total current should be 100. So 100 minus 4 is 96. So G is 5 into 96 by 4. 4 ones are 4 twos are 8, 4 fours are 16, and 5 fours are 20. 2 per 5 twos are 10, 11, 12. 120 ohm. The option is correct one. Okay. Next, a galvanometer coil of length 0.12 meter and width 0.1 meter having 50 turns of wire is suspended vertically in a uniform magnetic field of strength 0.2. The coil carries a current of 2 ampere if a plane of the coil is inclined at an angle of 630 degree with the direction of field and torque. Torque is basically M cross B, and M can be written as NIA, B sine theta. Now this loop with the magnetic field makes an angle of 30 degree. So the normal to the loop will make an angle of 60 degree. Remember that. Okay. Because normal is perpendicular to the plane. If plane is making an angle of 30 degree, so with the magnetic field and normal will make an angle of 60 degree, and this theta is that angle. So the number of turns is basically 50. Current is 2 ampere. Area is length into breadth, which is 0.12 into 0.1. Magnetic field of 0.2, and sine 60 is root 3 by 2. Okay, I think you can see 2. Okay, wait. Into root 3 by 2. This 2 and 2 is cancel each other. And let's 1, 2, 3, 4. 1, 2, 3, 4 zeros. And then 5 twos are 10. 2 into 50 is 100. So you are left with 12 and root 3. So root 3 is what? 1.732 into 12. Let's say 173 into 12. 12 3s are 36. 12 7s are 84. Plus 3, 87. 12 1s are 12. Plus 8, 20. 1.73 is a decimal here. And this 100 gives a decimal of 0.20. D is the correct option. Simple calculation. Next, an electron is released from rest in a region of uniform electric and magnetic field acting parallel to each other. Again, if the electric field and magnetic field are parallel to each other, the electron will moves in a straight line. Okay, that is moves in a straight line, because since the magnetic field does not change its direction if the electron comes in the direction in parallel or anti-parallel to magnetic field. And for the electric field also, it is a uniform electric field. So the force is uniform. It can accelerate it, but in the same direction. Now, if the electric and magnetic field acting perpendicular to each other, then there would be some deflection in electron and starts moving in a helical path. Remember that. But if both electric and magnetic field act parallel to each other, then moves in a straight line. Okay. Next, a straight current carrying conductor is placed inside a uniform magnetic field. The force per unit length acting on the conductor. The force is basically what? ILB sine theta. A straight current carrying conductor placed in a uniform magnetic field. The first point is maximum when the conductor is perpendicular to this. This theta is between the angle L and B. Okay. So theta would be 90 degree when L is perpendicular to B. That is, the conductor is perpendicular to the direction of magnetic field. Is along the direction? No. When the conductor is perpendicular, minimum? No, it should be maximum. And minimum, the conductor makes an angle of 45 degree. No. So A is the correct one. Next, an isosceles right-angled current carrying loop PQR is placed in a uniform magnetic field B pointing along PR. If the magnetic force acting on the arm PQ is F, the force here is F, and We have to calculate the force along QR. Now, if it is a isosceles triangle, then take this two length to be L and this become root 2L using Pythagoras theorem. Now, if you have to calculate the force across PQ, then it is ILB sine theta. Let the current be I, which is same in all the loops. L is L, B is B, and theta is 90 degree because the magnetic field and the Y PQ are perpendicular to each other, and become ILB, which is equals to F. Now, if we have to calculate the force around RQ, then it is again ILB sine theta. Here I is same. And the length will become root 2 times L. The magnetic field is same. And theta would be what? Here it is, if it take in opposite direction, it is minus 45 degree. So sine minus 45 degree, and sine minus 45 is what? Minus 1 by root 2. So this will become I root 2 LB minus 1 by root 2. Root 2 cancel, and it becomes minus ILB, which is F. So it is minus F. So D is the correct one. Okay, students. So the next thing is the current of 10 ampere is flowing from east to west in a long straight wire kept on a horizontal table. The magnetic field developed at a distance 10 centimeter from north on the table is. Okay, so the magnetic field, a current 10 ampere is flowing from east to west. Let's take the current which is flowing from east to west in a long straight wire kept on a horizontal table. Current I is given as 10 ampere. The magnetic field developed at a distance of 10 centimeter. At a distance of 10 centimeter due north, ऊपर की तरफ. Okay, so a long straight wire है, so considered as a infinite one. So B is basically mu naught I over 2 pi r, and you just put the values here. So B is equals to mu naught is 4 pi into 10 raised to the power minus 7. I is 10 over 2 pi, and r is the distance which is 10 centimeter, and we can put 100 above. Pi 2 0 0 cancel, 2 into 10 raised to the power minus 7 plus 2 is minus 5 Tesla. And for the current you can use like thumb here, finger is moving downward, cross. So it's 2 into 10 raised to the power minus 5 Tesla acting downwards. Okay. Next, an electron and a proton are moving along the same direction with the same kinetic energy. They enter a uniform magnetic field acting perpendicular to the velocity. The dependence of radius of the path on their masses. So radius is basically mv by qb. Okay. So the velocity is different, but if charge and magnetic field is same, so we can check the dependency of mass. So for the velocity, they are moving with same kinetic energy, that is half, let's say m1 v1 square for electron and half m2 v2 square for proton. So v1 square by v2 square is equals to m2 by m1, and the square will give you root here, and then you can just put it back here. So r1 by r2 radius is m1 v1 over m2 v2. m1 v1 is m remains same, and v1 v2 can be substituted with under root of m2 by m1. So this m1 to the power 1, and it is half. So 1 minus half is half. So it is this. That is basically r1 is proportional to m1 root and r2 is proportional to m2 root. B is the correct one. Okay, the next is so the next question says two wires carrying current I1, I2 lie one slightly above the other in a horizontal place as shown in figure. The region of vertically upward strongest magnetic field is. You can simply find the direction, and with that direction you will get the vertically upward field. So in the region 1, because of I1, the magnetic field is upward, and for I2, it's downward. So if both the current gives same magnetic field, there will be no magnetic field in region 1. For the second, first wire give upward, second is also give upward, so there will be net upward field. So it could be region 2. In third, the second will give upward, the first will give downward. You can use the right hand thumb rule, and with that you can get. And for fourth, again, the I1 will give downward, I2 will give downward. So this is a maximum downward field, but they have asked for vertically upward, so reason 2 is the correct one. Next, magnetic field at the center of a current carrying circular loop is of radius r is B1. The magnetic field at the point on its axis at a distance r from the center of the loop B2 is. So on the center is basically mu naught I by 2 capital R radius. And on the axis B2 is mu naught I a square over 2, and the distance is also r. So let's take this to be r square plus r square raised to the power 3 by 2. So it is mu naught I r square over 2. R square plus r square is 2r square. 2r square raised to the power 3 by 2. And then it gives you 2 root 2 r to the power 3. Okay. This will cancel, and then you can just take the ratio B1 and B2. B1 by B2, which is mu naught I over 2r into 4 root 2r by mu naught I. So it's simply 2 root 2. That is option A. Okay. Next question. A current carrying wire capped in a uniform magnetic field. It experiences a magnetic force when it is perpendicular. We have already discussed this many times. ILB sine theta. When L is perpendicular to B, then theta will be 90 degree. Force would be maximum. Perpendicular to magnetic field, parallel to magnetic field at an angle of 45 degree, at an angle of 60 degree. So B is the correct one. If an ammeter is to be used in place of voltmeter, then we must connect with an ammeter a shunt resistance of low value in parallel, and for voltmeter, shunt resistance of high value in series. A low resistance in parallel will help you in ammeter, and high resistance in series will help you in voltmeter. Always remember. Fine. A flexible conducting rod of length L, mass M, is suspended in a horizontal plane of a pair of flexible string and a magnetic field of magnitude B. To remove the tension in the supporting strings, the magnitude of current. Okay, so you have a conducting rod of length L, mass M, some, and carrying some current I, and this mass have already this mg downwards, and there is a magnetic field. To remove the tension, see there is tension as well, and if you have to remove the tension, then this basically mg is equals to tension, and to remove the tension it is replaced by the force, magnetic force, which is ILB sine theta. Okay, and for the maximum support, leg theta to be 90 degree, then mg is equals to ILB, and your I will be mg by LB. mg by LB, which is option number C. Which of the following statement is correct? Magnetic lines do not form closed loop. This is wrong. They form a closed loop. Outside the magnet moves from north to south pole, and inside south to north. So magnetic field starts from north pole and ends in south pole of a magnet outside, and inside south to north. So it is incomplete. The tangent at a point of magnetic field line represents the direction of magnetic field. Yes. And the tangent to a point on an electric field lines gives the direction of force. Okay. Two magnetic lines may intersect each other. No, they cannot intersect. Okay, the next is a proton and an alpha particle moves in circular orbit in a uniform magnetic field. Their speeds are in the ratio V proton by V alpha is 9 by 4. The ratio of the radii of the circular orbit. So radii is mv by qb. The magnetic field is same, so only we have to check mv and q. M proton by mass of alpha, then velocity of proton upon velocity of alpha, and charge is down, so charge of alpha upon charge of proton. Okay, just put the values, and if the mass of proton is m, then the mass of alpha would be okay 4 times the mass of proton. Okay, velocity of proton, velocity of alpha is given as 9:4, and for the charge of proton is q, then alpha would be 2q. Okay, for alpha the charge is double and mass is 4 times, then q cancel, mass cancel, 2 ones are 2 twos are 9 upon में 4 twos are 8, so 9/8 is the ratio. Okay, then the current sensitivity of a galvanometer increases by 20%. If its resistance also increases by 25%, the voltage sensitivity. Voltage sensitivity is current sensitivity by resistance. Now its IS is increased by 20%. So new IS dash would be what? IS plus 20%, that is IS by 4. 20 into 100, let's say 20 by 100 times of I karoge, so you will get 1/5. And you can add, so you will get the new IS. 5 plus 1, 6, IS by 5. Okay, and the resistance is also increases by 25%. So if the initial resistance is R, then on increasing it by 25% is 25 by 100 into R. 4 that is R by 4. So you can add R by 4. LCM 4 plus 1, 5 R by 4. Okay, so now V dash will come IS dash by R dash, which is 6 IS by 5 over 5 R by 4. And if 4 goes up, 6 4s are 24 by 25 IS by R, which is original V. Okay, so for the percentage, it's simply V minus V dash by V into 100. So because V dash is less, 24 by 25, 25 denominator is higher, so V minus 24 by 25 times of V over V into 100. So you can cancel V. 25 minus 24 is 1. 25 4s are, so 4%, and because V dash is less, so it is decreasing, so decrease by 4%. Simple maths hai. 3 infinitely long parallel straight current carrying wires ABC are kept at equal distance from each other, shown in figure. The wire C experiences a net force F. Okay, so the net force on wire C when the current in the wire A is reversed. Okay, so force on C due to B and A दोनों निकाल लेते हैं. So force on C in the second condition when the current in wire A is reversed, I'm calculating that. So B is same, so it should be, you have to calculate force. So mu naught I1 I2 upon me 2 pi A is the force per unit length formula. So it's mu naught, this is I square over 2 pi R, because the distance between these two is R. And if you have to calculate the force, since the current are parallel, so it attract towards it. It is in this direction. Let's say minus I cap. It will attract. The parallel current attracts, the anti-parallel repel. Now the current in A is reversed. So the current will become mu naught 2I into I is 2I square upon 4 pi. The distance is R plus R, 2R, and it's plus I cap, because here the force will be in opposite direction because the anti-parallel current repel each other. So these two terms are exactly same, mu naught I square by 2 pi, mu naught I square by actually it is 2 pi R only. 2 pi and the distance is 2R. So it exactly same. This is minus I cap, this is plus I cap, so the net force would be 0. But if it is not 0, then you can relate it with F. So you have to calculate it before the current direction in A changed, and then you can compare. Okay. Beam of electrons and protons move parallel to each other in the same direction. Electrons are moving this, protons are moving this. So the current is moving in this direction, I, and here the current is moving in this direction. So the currents are anti-parallel, they repel each other. They attract, they repel, neither attract, repel. Force of attraction, repulsion depends upon, no. They repel each other. Okay. Next question. A long straight wire of radius A carries a steady current I. The current is uniformly distributed across its area of cross section. The ratio of magnitude of magnetic field B1 is A/2 and B2 at a distance of. Okay, it has the same mechanism as we did earlier, which I've told you in the first question. So it's a long straight wire, let's say, of radius A and carries a current of I. The current is uniformly distributed across its area. The ratio of magnetic field at A/2 and 2A. So when it is at A/2, so you have to calculate it using Ampere's circuital law. First you have to calculate current. So current upon area into the area of A/2. Okay, that means the current flowing in the Ampere's loop. Okay, so this becomes I/4. So your B1 into dl, that is the length of the Ampere's loop. Here the Ampere's loop has the radius of A/2. So 2 pi into A/2 is equals to mu naught I enclosed, and here I enclose is I/4. Okay, you can cancel 2, and then B1 would become, B1 is mu naught I/4, and this pi A goes down. Okay, now for B2, this has a radius A carrying current I. Now for B2 is a distance of 2A. Now if you take a loop, the current total I would be there, I enclosed. So here B dot dl, here dl would be 2 pi into 2A, because the radius is 2A now, is equals to mu naught I enclosed. I enclosed is I because whole of the wire is coming inside 2A. Earlier only A/2 is coming, so we have to find the current flowing in A/2 if a uniform current is flowing through the wire of radius A. So you have to use current density thing, means current per unit area, then you have to multiply the area of Ampere's loop. So here also B2 comes out to be mu naught I over 4 pi A. So B1 and B2 both are same if you take the ratio at 1:1. Fine. Which of the following graph correctly represent the variation of magnitude of a magnetic field outside a straight infinite current carrying wire? So outside is basically is inversely proportional to the distance. So it is something like this. So they have asked only outside. It's not straight, and here also it's not like this, it should be straight. It should be like this. Okay, so this is the appropriate one. At the center it's 0, then it varies linearly, and outside it varies inversely. Okay, so the last question. An electron enters a uniform magnetic field with speed v. It describes a semicircular path and comes out of the field, the final speed. See, the uniform magnetic field does not accelerate the electron, does not change the velocity of the electron. So if it making an semicircular path also, the speed will remain same. So if it enters with v speed, it leaves with v speed. Okay, so this is much for moving charge and magnetism. This is one of the most important chapter. It has many concepts, and yeah. So thank you for watching this video, and do like, subscribe and share and comment below, and yeah, we'll meet you in the next video.